Alright, physicists, welcome to our review for Unit 2. In this review, we're going to be going over ideas about capacitors, resistors, current, and circuits. Now, the equation sheet that I've given you for the test is fairly full. It has stuff with resistors, capacitors, it has stuff on Kirchhoff's laws, on RC circuits, on the relationship between the electric field and the electrical potential. Now, depending on how closely you've been paying attention in this class, you might say, that's way too much. On the other hand, you might be looking at this and say, well, this is all stuff we covered. And I say, yeah, I agree. No problem. Probably, if you're watching this video, you are somewhere in between. Okay, so in this video, what I'm going to try to do is go and step by step cover a lot of the stuff that we went over in this unit and break it down and do a few quick problems for each idea. So here's a capacitor, all right, just a sheet of metal, a space, and another sheet of metal. Okay, so a conductor, an insulator, a conductor. And typically you put a positive charge on one of those conductors, a negative charge on the other, such that the capacitor has an overall charge of 0. And then think about what voltage difference there is across the plates. Okay, and conversely, you can think about putting a voltage difference from a battery across those plates, and then that would predict what kind of charge. And the equation here is Q equals CV. So here's a quick example. 150 microfarad capacitor is fully charged when it has 6.1 times 10 to the third coulombs across its plate. What is the potential difference across the plates of the capacitor? Well, you can always use Q equals CV, and you could go ahead and find that V equals Q over C, and then just plug in the numbers. And then we'd put 150 times 10 to the minus 6 farads. And so then we would find a voltage that's somewhere in the 100 volt range. And so you're going to just stick in the numbers. And for those of you who are taking this course, I have provided a review sheet that does have a solution manual that I made up with it. And so the key on a test is to make sure that when you see a micro, you can already convert that to 10 to the minus 6. Here, this could also be you could have a millicoulombs. But if you want everything to turn out to have good units, so our good units on charge are coulombs, our good units on capacitance are farads, and our good units on potential difference are volts. If you want all of those to just stay in their standard way, you're going to have to do those metric prefix conversions. So another type of question I could ask you on capacitors, you'll remember way back at the beginning of this unit, we derived the equation for the capacitance of the two charges separated on opposite plates. And essentially, it was a approximation, because you can find the electric field in between two infinitely big parallel plates, and then you can find the voltage by integrating over the electric field, because electric field in the y direction, for instance, would be related to the derivative of the potential. And then so we could say that if we wanted the potential difference, which we then sloppily just write as V instead of delta V, we could go ahead and take the integral of that minus potential over minus 0 to D and dV dy. Okay, so we basically integrated the potential, or whoops, what am I doing? We integrated the electric field. We integrated the electric field over this distance to go ahead and find that difference in potential. Okay, so that's how we got this result, and we found this capacitance in terms of essentially something that looks sort of like a surface charge density. But for now, what we need to realize is that the area is up here in the numerator, and the distance between the plates, so that's d, and then the area, if this was just length times width, it would be length times width. So here it says, consider a parallel plate capacitor. How does its capacitance, that's C, how does the capacitance change if the distance between the plates doubles? Well, if the distance between the plates doubles, you get a factor of 2. So your C prime here would be epsilon naught A over 2D. So I hope you can see that the capacitance then would drop in half. If you put the same amount of potential difference across the plates, you would get half as much charge. So that's what that means. And then it says, what is the capacitance of two metallic squares 1 millimeter on each side that are separated by 3 micrometers? Okay, so that in a sense is just a plug in the numbers. Look up your epsilon naught. I'll give you that number. Look up, and then you have to just plug in A and D. Okay, so a problem like this is really just using this formula, and the A in this case would be 0.001 meters squared. Okay, so this is one that I know I'm going to see a couple people on the test flub, because when they put in A, they just put in the size of the length. They don't do a length times width. And then of course when you put in the D, you also want to put that into good units. So our D here, 3 micrometers, would be 3.0 times 10 to the minus 6 meters. Okay? Now, when we went from capacitors, which just store charge, to resistors, which have current running through them, so charge per unit time is going through that surface. Remember, current is measured in amps. Amps is coulombs per second, so you're essentially counting how much charge passes by your surface each second to get amps. That current is taking into account all of the charge that passes through a particular point in your wire. Now, we could also think about current being split up into some sort of a current density, J, and that J is in terms of current flowing per unit area. And so in a problem like this is a homework problem that I gave you a while ago. It says a current of 2 amps runs through a circular conducting wire with a diameter of 0.5 centimeters. So if we had this as a genuine problem, I've given you a problem on your review sheet that's similar to this with just a slightly different numbers. So there's a 0.5 centimeters. Your R would be 0.0025 meters. The area of that surface would be pi times R times R. And then if you ask A, how many electrons are passing through any cross-section of the wire per minute? Well, you have I is 2.0 amps. And of course, we're seeing our perennial problem here, which is that we have variables which also look like they have the same units, same symbol as the units. Ugh. But in any case, for our how many electrons are passing through any cross section of the wire per minute. That would be a question about current. And if we have 2 amps, you'll remember what we did here. We had amps is coulombs per second, and we had 60 seconds in 1 minute. And then we could convert from coulombs to electron charges by saying that 1.602 times 10 to the minus 19th coulombs is 1 electron charge. And then our seconds canceled out, our coulombs canceled out, and we got electron charges per minute. Okay, so that is one sort of puzzling thing about current for us to remember, is that if we have a current going this way, it means that the electrons are actually moving the other way because they have a negative charge. We could also get that current by having the plus charges move in the direction, but in fact the thing that's moving are the electrons. Okay, and then B, assuming that the current is uniformly distributed through the wire, what is the current density J in the wire? Well, J I would get by just putting that I, remember this is intensity de courant from Ampere, so there's I over A. Okay, so this would be 2 amps over 3.14 times 0.0025 squared, and then that would give me meters squared. So I get an answer that's big in amps per meter squared. All right, now throughout our current or our circuits unit, we've sort of moved away from thinking about things in terms of the electric field, because electric fields are harder to measure in the lab than potential differences. Potential is a number, electric field is a vector. So often we talk instead about potential differences, realizing that we could translate back into the language of electric fields. So remember, the relationship between electric potential and electric field is this. If you want to find the electric field in a particular direction S, what you'd need to do is define how is the potential changing in that direction per unit distance. So volts per meter is a perfectly legitimate unit for electric field, even though the original units that we found, so this is volts per meter, the original units that we had were newtons per coulomb. This is telling you how is the potential energy per charge changing per meter. This one is telling you the force that you get per charge, but it turns out those are equivalent ideas. Now, this question asks, wires A and B are identical except that the length of wire A, so here's your A, is 1/2 that of wire B. So here's your B. If the same potential difference is applied between 2 ends of each wire, how does the electric field within wire A compared to that within wire B? Okay, so let's look. Wire A has a length, let's say, of 1 meter. Wire B has the a length of, let's say, 2 meters. I'm just making up numbers that are plausible. Here, let's say that we have a 10 voltage difference from some battery. And here, let's again consider that we have a 10 volt voltage difference from the battery. Now, what would the electric field within that wire look like? Well, in A, the electric field along A would give me that, well, here's your positive to negative electric field flows downhill, so your electric field would be in this direction. Electric field would be in from high to low, high potential to low potential. And in your A example, it would be 10 volts per 1 meter. In EB, it would be 10 volts per 2 meters, or it would be 5 volts per meter. So if you just stick in those numbers, I hope it's easy to see that EB is about 1/2 of EA. So the electric field is going to be it's going to be lower in the second case, but whether or not that changes the current, you have to think about the overall resistance rather than just the electric field. Okay, so remember, resistance depends on a bunch of things. It depends on the resistivity of the material. It depends on how long your sample of the material is. It depends on the cross-sectional surface area. But if you roll all of those things together, you get a simple relationship for certain types of objects called ohmic resistors, and this is Ohm's law. And that's what you should remember very well for this test. Okay, so when a potential difference is applied to a certain copper wire. So now we're talking about a specific copper wire. We're not talking about copper in general. And it says a current of 1.5 amps passes through the wire. Coulombs per second, I is current. If the wire was removed from the circuit and replaced with a copper wire that was of twice the diameter, what current would flow through the new wire? Okay, well, we're saying that V equals I times R, right? And we're assuming that we're keeping the potential difference the same, but we're changing the diameter. Okay, so let's think. I equals V over R. So it's going to be V. Let's use this model now. Okay, so V over resistivity, length, area. And I'll just rearrange that a little bit. V times area over resistivity times length. So it asks the question, if it were replaced by a copper wire of twice the diameter. So if I go from pi r squared, okay, d is r over 2. So if I go twice the diameter, you also get twice the radius. So in that case, I would go pi 2r squared. And that would be 4 pi r squared. So if I double the diameter, I quadruple the area. And so for part A, your I at the end with that new wire is going to be 4 times the initial current. Okay, so it's going to be 4 times 1.5, that would be 6 amps. So on the other hand, for part B, they ask if the wire was removed from the circuit and replaced with a copper wire of twice the length, what current would flow through the new wire? Well, if you had 2 times the length, 2 times the length would lead to half of the original current, because this is replaced with a 2L, so this whole thing goes down by a factor of 2. So this changed current would be 1/2 of your I, or 0.75 amps. Okay, so that's fair game. Now, so any question about V equals IR is fair game. Questions about how resistance changes when you change the length of the resistor or the cross-sectional area or the resistivity, that's all fair game. The other thing that's fair game in this test is talking about resistors or capacitors in parallel and series. So what happens in series? Well, so I'll give you these formulas, but if you haven't had some practice with them, those could look pretty forbidding, pretty arcane. So let's remind ourselves how to use this. It says, consider the circuit shown if the ideal EMF of the circuit is 12 volts and the three resistances are 3.5 ohms, 6 ohms, and 8 ohms. Determine the current in R1. How does this compare to the circuit's currents flowing through R2 and R3? Well, the second part of this is the easier part. If you have current going through this circuit, the analogy that we've tried to develop here is that this is sort of like a water pump, and each one of these resistors is sort of like a kink in the pipe. And so the same water flowing through the first one has to flow through the second one, has to flow through the third one. So if I find the current in R1, it should be the same as the current through R2 and R3 because it's not branching off anywhere. We've also argued in Kirchhoff's laws that this is sort of another way of expressing charge conservation. So in this case, what I would need to do is I would need to find the equivalent resistance and then use the voltage to find my circuit current. Okay, so this equivalent resistance for a resistors in series is just going to be the sum of all of the resistors. So it would just be 3.5 plus 6 plus 8 ohms. Okay, so that would be 9.5 plus 8 is 17.5 ohms. And then if you wanted to find the current, you would just use the battery voltage, and V equals I times R equivalent. Because remember, if you measured the potential drop across each one of these resistors, it would be less than 12. The sum of the drops over these resistors would equal the sum of the potential rise across the battery. So what you would need to do in the next step is just say that I equals 12 volts over 17.5 ohms. And so volts over ohms gives you amps. Now the difference for resistors in series and capacitors in series is not a lot in terms of the concept, except instead of having current going through, you have charge that's stored on the capacitor, on the capacitors. So in this case, you have a 1 microfarad, a 2 microfarad, and a 3 microfarad capacitor, and they're connected in series. Each one of these will have a different voltage drop across them, but the sum of the three drops will equal the 100 volts provided by the battery or the voltage source. And then it asks, what is the equivalent capacitance of the three capacitors combined? Well, there's nothing tricky about this except using the formula. So 1 over C equivalent is 1 over 1 microfarad plus 1 over 2 microfarad plus 1. So I've done this calculation before. It might be worthwhile, if you're doing this in your test, simply to plug this into your calculator, plus plug that into your calculator, plus plug this into your calculator, and then take 1 over the quantity that you've found. And then that would give you your C equivalent. On the other hand, if you wanted to work it all out, you could So that would be your 6 over 6 plus 3 over 6 plus 2 over 6 equals 11 over 6 microfarads, or your equivalent charge is just going to be 6 over 11 microfarads. The thing to notice that's important here is that that is smaller than 1. And it's smaller than 2 and it's smaller than 3. So the equivalent capacitance of a bunch of capacitors in series is going to be smaller than the capacitance of any one of the capacitors in your circuit. If you wanted to find the charge on any one of the capacitors, if they start out uncharged, they will all have the same amount of charge at the end, and you would find that by taking Q equals C equivalent times V battery. Okay, so 600 over 11 microcoulombs would be your answer, because you just take this number times that number, and it would give you an answer that's a charge in coulombs. Now, the problem is a little different when we have something in parallel. And the reason it's different fundamentally is that the charge, the voltage difference across each element is the same. Okay, let me say that again. When you have elements that are in parallel, the potential difference across each element is the same. And so you'll remember this was a homework problem, or maybe it was just a problem I showed in class, where we had the same amount of voltage across each one of these items. We had 60 watts was the power. We had that 120 volts was the voltage, and we know that P equals I times V. And then we went ahead and used V equals IR and put in V over R for the I to get that P equals V squared over R. And I think you can remember, whoops. So let's do it a different way. V equals IR. So you can just put in that. So this would be I squared R. And then you could go ahead and I think I'm confusing myself here. Oh, yeah. Wait. Okay, yeah, I have to think before I speak, but then these videos would get even longer than they already are. So, yeah, we already have everything we need here. Then we went ahead and found what the current through each bulb was, just by using this. So I equals P over V. So your I is 0.5 amps. And so the idea is that you've got 0.5 amps going through each one of these wires, but so I should draw that with the current going from plus to the minus direction. So, but as you add another wire, you get another 0.5 amps. So we can represent that here with like 2 arrows. And each of those adds to the total current coming out of the battery at the beginning, 0.5 amps. So here, if we just had 3 bulbs, we would have 1.5 amps coming out of that battery, coming out of the voltage source. And so if you can go up to 9 amps, that means you can get 18 bulbs. Okay, so we did that problem earlier. I just want to remind you that the key idea is in parallel, you have the same voltage, and you get it could be a different current for each one depending on if you use different resistances for each one of the bulbs, for instance. So here would be a nice example for resistors in parallel. Again, I've sort of dropped the ball because I made them both 20 ohm resistors, but that's okay. So there's a 20 ohm resistor, another 20 ohm resistor. It says a potential difference of 9 volts is applied across. What is the equivalent resistance of the system of two resistors? Well, you could use your equation and say that 1 over the equivalent resistance is 1 over 20 ohms plus 1 over 20 ohms, which gives you 2 over 20 ohms, which gives you the equivalent resistance. Now I'm going to flip both sides of this. Req equals 20 ohms over 2, which is just 10 ohms. So there's my first part of this type of a problem. And then it asks, what is the resulting total current that flows through the two resistors? Well, in that case, you might go ahead and use your V equals IR, where I then would be the current coming out of the battery. So V equals IR. So this is B battery, and this is R equivalent. So in that case, your I total would be this 10 ohms. It would be your 9 volts over 10 ohms, 9/10 amps. On the other hand, if it asks what current flows through each individual resistor, well, that you would just use your V equals IR, where you know the V across each one, you know the R of each one individually. So in that case, you would get I for each individual resistor. It would be 9 over 20 amps. Now, what's the relationship? If you took 9 over 20 plus 9 over 20, you'd get 9 over 10. Okay, so the way that you get the circuit current here is just by adding up the current through each one of these. So there's your I1, here's your I2, and the thing coming out here is I1 plus I2. Now, in capacitors in parallel, it's a little easier in terms of the equivalent resistance the equivalent capacitance, because these are all just storing a separate charge. So the potential difference across each of the capacitors, if you have a potential difference in the battery of 100 volts, is just going to be 100 volts. If you wanted to find the charge on each capacitor, it also would be easy, because you could just use Q equals CV for each one of these individually. So for B, if you wanted to look at the 1 microfarad capacitor, you could find the Q equals CV just by doing 1 microfarad times 100 volts, and then the Q would be 100 microcoulombs. Or if you if this were a multiple choice question, for instance, that might be 10 to the squared. 10 squared times 10 to the minus 6 coulombs is 10 to the minus 4th coulombs. 1 times 10 to the minus 4th coulombs. So there'd be different ways that you could put that. And then the easier problem is, what is the equivalent capacitance of the 3 capacitors combined? Well, remember, in parallel for capacitors is actually where you get the easy equation, where the equivalent capacitance is just taking your 1 microfarad plus 2 microfarad plus 3 microfarad. Okay, so if you're doing the capacitors in parallel, that's when you just get to add up the capacitance of the individual capacitors. And that's where we're treating these 3 capacitors as 1 capacitor combined. Okay, now The last point of comparison between capacitors and resistors is that for resistors, they are using energy, they're dissipating energy, taking the energy from the battery, and it will leave the circuit in terms of, either work that's done by a motor, if you're, modeling a motor that way, or in our case, our simple case, just heat. Okay, so the P equals IV equation for a resistor, power is in watts, which is joules per second. It's telling you how much energy is leaving your circuit per second. And P equals IV can be used across a circuit component, and there are different forms of that, as you saw on your quiz last Friday. So let's take a look at this question and try to think about how power is dissipated differently in series circuits and parallel circuits. So it says 2 light bulbs, one 50-watt bulb and one 100-watt bulb, are connected in parallel with a standard 120-volt AC electrical outlet. The brightness of a light bulb is directly related to the power it dissipates. Therefore, the 100-watt bulb appears brighter. How does the brightness of the 2 bulbs compare when these same bulbs are connected in series with the same outlet? How does their current compare? Okay, so let's draw this situation out. 50 watts and 100 watts. So I have a 50 watt and a 100 watt bulb. And I can have them connected in series, or I can have them connected in parallel. Now, this is sort of a fiendish problem. I am not going to give you something this hard on the test, but it is worth thinking about. The reason it's a little fiendish is that the wattage has to do with a given voltage. So they're already assuming that there's some sort of given current that's causing some given current and voltage that's going to be causing that wattage. So if you use a standard voltage, okay, if I use a standard voltage, would a larger number of watts go with a larger or a smaller current? Well, if you use a standard voltage, the bigger power is going to go with the bigger current. So if you have a bigger current, does that mean that you have, so bigger wattage goes with bigger, so 100 watts typically would go with a bigger I, and 50 watts would go with a smaller I. But if I have a big I, a big current, that means that you have a small resistance. If you have a small current, that means you have a bigger resistance. So the sort of fiendish way to think about this is that you could figure out what the current is in this sort of a problem, because you would assume that you'd have 120 volts. So in this case, for instance, the smaller current through the 50 watt would lead this to be dimmer and lead this to be brighter. Okay? Because, so this would be brighter and you'd get a bigger I. Here you get dimmer and you get a smaller I. But in this case, in the 50 watts and 100 watts, they're in series, so they have the same current going through each one of them. Okay, and if you have the same current going through each one of your circuit elements, then the situation's a little different, because then you have, for instance, P equals I squared R. So if you have the same I, the one with the bigger resistance is going to have the bigger power. Okay, bigger resistance is bigger power. So the 50 watt is going to have the big R. In this case, it's going to be bright, and this has the small R, and so this one is actually going to be dim. Okay, so it's a little bit confusing, because if you have these two, the bulbs that are in series, where they're both bright, where one is bright and one is dim, then you put them, if they're in parallel, one is bright and one is dim. If you put them in series, they'll flip-flop. Okay, so that's an interesting problem, maybe a little bit too hard to put on a test. On the other hand, let's think about energy stored by a capacitor. Okay, now this would be the easier problem. You could think about adding up the energy of each one of the capacitors. So the energy stored by a capacitor, 1/2 CV squared. Here we've got three parallel plate capacitors. They're wired in parallel. Potential difference is 100 volts. Now, if we wanted to find out how much energy, electrical energy, is stored overall in the system of capacitors, I could take 1/2 times the 1 microfarad times 100 volts squared, and I could find the energy on the first one. Then I could do the same thing and find the energy on the second one, and then I could find the energy on the third one. That would be fine, and then you could add the three energies up to get your overall energy. On the other hand, you could also go ahead and use your equivalent capacitance of 1 plus 2 plus 3 microfarads equals 6 microfarads, and then find the energy stored in this whole circuit as 6 microfarads. So I'm going to put in 10 to the minus 6 times 100 volts, and I'm going to have to square that, so I'm going to have 10 squared volts. Okay, so this is 10 to the minus 6 plus 2 plus 2, so that gives me 3 times 10 to the minus 6 plus 2 plus 2 gives me minus 2 joules. Okay, so those are just two ways of thinking about the same thing. Okay, so our last topic I want to discuss just a little bit is RC circuits. We only briefly went over these on Friday. And the basic idea is that if you flip an RC circuit on, it will charge up. So over time, it will eventually get to a point where it reaches a charge of where this capacitor reaches a charge of Q equals C times V. So here's your Q. And we related that to the current that's flowing through the resistor, and you can solve for that Q using a differential equation. Now, the key thing in these RC circuits is to realize that the time dynamics are determined by the product of R times C. because if you have a resistor whose resistance is large, it will cause the current to be smaller. If you have a resistance whose resistance is small, it will cause the current to be bigger. A small resistance allows this capacitor to charge more quickly. A big resistance allows this capacitor to charge more slowly. And so what we're looking at with this T is how long does it take that capacitor to achieve its final charge for a given voltage. On the other hand, the reason why the C is in there is because if you have a bigger capacitance, you can get a bigger current, or sorry, a bigger overall charge that's sitting on that capacitor for a given voltage. So both of those things matter. So that's the charging circuit. T equals R times C also commands the dynamics of the discharging circuit. So if this is charged up and then I close this charge, then I would get a current going the other way, and my charge on my capacitor would begin to drop like this and go down to 0. So you start at some Q equals C times V at the beginning, and then that would be your Q naught, and then you discharge and you get smaller and smaller and smaller amounts of charge as that current flows through the resistor. Okay, so let's just look at one quick problem that I said. You have 2 resistors, 2 capacitors, and 2 batteries. The resistors have resistances of 10 ohms and 100 ohms. While the capacitors have capacitances of 5 microfarads and 50 microfarads. Both batteries supply a voltage of 12 volts. Using these resistors and capacitors, draw one RC circuit whose capacitor reaches its final charge more quickly, and one RC circuit whose capacitor reaches its final charge more slowly. Well, the only thing to realize here is that the dynamics depend on R times C. So, if you have want one to charge more slowly, you'd want a smaller if you wanted it to charge more quickly, you'd want a big RC. So quick, you would want to have a quick charge would be a small time constant. If you wanted to have a slow, you would want to have a big time constant. Okay, so in the RC circuit looks like battery, and then a switch, and then a resistor, and a capacitor. Battery, switch, resistor, capacitor. And in the first case, if you want a small time constant, you would want to have a small resistance and a small capacitance. Okay, so this would allow the charge to pass through the resistor quickly, and your capacitor would not hold very much charge, so that would go ahead and charge to its final state pretty quickly. And the final state would only hold 5 times 12, so 60 microcoulombs of charge. On the other hand, if you wanted a slow charging, what you'd do, you'd have 100 ohms and 50 microfarads. So this one, instead of holding just 60 microcoulombs of charge, it would hold 600 microcoulombs of charge, and the amount of initial current that would be produced would be 10 times smaller because you have a bigger resistance. So bigger resistance means that you get less current. Bigger capacitance means that you get a bigger charge, and that means that your eventual current persists for longer. Okay, so I realize as this video has gone on, the ideas get a little bit more hairy, but I think that if you go ahead and you work through the review sheet completely and try to get all the answers that I've gotten, you're going to do really well on this test. And so remember, you've got to understand capacitors, you've got to understand current, you've got to understand resistors. Think about how capacitors store energy, resistors dissipate energy. Think about the difference between parallel and series for each, and then just a little bit about RC circuits. Secretly, we're not going to don't really worry about Kirchhoff's laws. And that's it. That's Unit 2. So good luck studying. If you have any questions, I'm around.